Hello, everyone. In this work, we propose a method exploring instance relation for decentralized multi-source domain adaptation. For the conventional multi-source unsupervised domain adaptation, there are multiple labeled source domains and an unlabeled target domain. The distribution of unlabeled target domain is different from the distributions of source domains. The multi-source unsupervised domain adaptation aims to learn a model working well on the target domain knowledge from the source domain and reducing the domain gap between the source domains and target domain. The conventional multi-source unsupervised domain adaptation method assumes that the source domain and target domain can be accessed simultaneously for conducting domain alignment, but considering the data privacy-preserving restrictions. Source domains and target domain are isolated and cannot be accessed simultaneously. This decentralized multi-source unsupervised domain adaptation brings a great challenge for conducting domain alignment. In this work, we focus on the more challenging decentralized multi-source unsupervised domain adaptation. For the conventional multi-source unsupervised domain adaptation, the centralized paradigm conducts domain alignment by reducing the statistic discrepancy or adversarial manner. The source-free paradigm firstly pre-trains the source models only on the source domain. Then the source models are fine-tuned on the unlabeled target domain distribution. The collaborative paradigm collaboratively trains the decentralized source domains and target domain under the federated learning paradigm, E.G. Fed average by local training and global model aggregation. In this work, we utilize the collaborative paradigm to solve the decentralized multi-source unsupervised domain. Our method has the following motivations. 1. Data from different domains cannot be exchanged, which brings a great challenge for reducing the domain gap between source domains and target domain. So we use the models from other domains as bridges for transferring knowledge and conducting domain alignment. 2. Considering the intrinsicship among samples should be invariant across different domains. We propose interdomain instance relation consistency to transfer the instance relationships across different domain models. 3. Considering the semantic relationships among samples should be invariant to the changing of data views. We propose interrelation consistency to learn the invariant instance relationships across different views of sample. Our method iteratively conducts local model training on isolated source domains and target domain and global model aggregation. There are 5 steps in each round. Step 1, local training on source domains. Step 2, upload the local source domain models to the target domain. Step 3, local training on the target. Step 4, model aggregation by parameter averaging. Step 5, upload the local target domain model and global model to source domains for the next round of. For the local source domain training in Step 1, the overall loss is shown in equation 1, where the LCE is the standard cross-entropy loss on the labeled source domain, the LS inter and LS intra is the interdomain and intradomain instance relation consistency loss respectively. Lambda S inter and lambda are the hyperparameters. The LS inter is shown in equation 2, the HIJT is the scaled feature cosine similarity extracted by the offline local target domain model, the SIJS is the feature cosine similarity extracted by the online local source domain model. The LS intra is shown 3, the HIJS is the scaled feature cosine similarity extracted by the offline local source domain model. The SIJS is the feature cosine similarity extracted by the online local source domain model with strong data. For the local target domain training in Step 3, the overall loss is shown in equation 4, where the LPL is the standard cross-entropy loss on the pseudo-labeled target domain, the LT inter and LT intra is the interdomain and intradomain instance relation consistency loss respectively. Lambda T intra are the hyperparameters. The LT inter is shown in equation 5. The bar HIJS is the scaled averaged feature cosine similarity extracted by the offline local source domain model. The SIJT is the feature cosine similarity extracted by the online local target domain model. Intra is shown in equation 6. The HIJT is the scaled feature cosine similarity extracted by the offline local target domain model. The SIJT is the feature cosine similarity extracted by the online local target domain model with strong data. In step 4, we average the local source domain models and local target domain model by parameter averaging as shown in equation 7, where Ni is the number of samples from source domain I, and T is the number of samples from the target domain. The N total is the total sample number from source domains and target. After model aggregation, the global model MG is uploaded to source domains for the next round of training. We conduct experiments on MSDA datasets such as Digit 5, Office 31, and Office Caltech 10. The results show that our method outperforms other SOTA MSDA methods significantly, including conventional MSDA methods under the data centralization setup and decentralized MSDA method decentralization setup. The feature visualization indicates our IRC MSDA method can capture the manifold structure of data and reduce the domain gap between source domains and target. Conclusion 1. In this paper, we propose an instance relation consistency method for decentralized MSDA. 2. For reducing the domain gap between source domains and target domain, we propose interdomain instance relation consistency. 3. For maintaining the intrinsic semantic relationship within, we propose intradomain instance relation consistency. 4. The results on standard MSDA datasets indicate the effectiveness of our. Thanks for your listening.